Now, about today's presentation. Our speaker, Karl Rijkse, has studied organic and analytical chemistry at the University of Amsterdam. He then moved to London, England, and enrolled at the Hurley Management College, where he studied strategic management. His last position before retirement was as Vice President of Technical Sales and Research and Development for Tiger Coatings. However, he is here today to talk about all things astronomy, which is what inspires him. He's, as you will find out, he's not only a member, but he's now the president of the Shoreline Amateur Astronomical Association based in Hemlock Crossing, and where there is an observatory that he will talk about, and the planetarium is also available, or will become available to us as well. And HASP members have been to the planetarium to view a program there. Canadian singer-songwriter Joni Mitchell wrote a song titled Woodstock to commemorate the event. You're all familiar with it. In the chorus, she writes, "We are stardust. We are golden. We are billion-year-old carbon." She's referring to the fact that mankind is connected to the physical world. Neil deGrasse Tyson said, "We are part of this universe. We are in this universe." But perhaps more important than both of those facts, the universe is in us. Stars have been a topic of astronomy for millennia. 100 years ago, scientists did not know that stars were powered by nuclear fusion. 50 years ago, they did not know that stars are continually forming in the universe. Researchers to this day still do not exactly understand the details of how clouds of dust and gas collapsed to form a star. Three astrophysicists shared the 2020 Nobel Prize in Physics for their work on the most exotic phenomenon, perhaps, in the universe, the black hole. British scientist Roger Penrose showed that black holes are a direct consequence of Einstein's general theory of relativity. German scientist Reinhard Genzel and American Andrea Ghez discovered that an invisible and extremely heavy object governs the star's orbits in the center of our Milky Way. A supermassive black hole is the only currently known explanation. Still some obscurity about that, pun intended. So join me in welcoming our guest, who will discuss the stages in the life of a star, from its birth from a cloud of dust and gas to its possible end as a black hole. Karl Rijkse.
Thank you very much, Louis. Thank you for the kind introduction. I should be on. I'm on, yes, okay. A little bit more volume, good, no problem. I hope you can understand. The 1 o'clock presentation is most of the time the most challenging because it is after lunch, nap time. So let me try to make sure that I engage you enough to keep you awake. And the other thing, it's today, September 22nd. You probably know that. It's also autumn equinox, which means that the 2:19 Eastern Standard Daylight Savings Time this afternoon, the sun will cross the celestial equator. Day and night are roughly the same length, and autumn starts today. The Shoreline Amateur Astronomical Association, which is a mouthful, we call it SAAA, about 60 members, mainly in the Holland, Grand Haven, Allendale area. We have a nice observatory at Hemlock Crossing Park in West Olive. Some of you visited us already every Friday night, public observing. And October 4, we are open from 12 till midnight because of Astronomy Day. Non-profit organization, Started in 1989. I'm the current president. A lot of people went before me. Planetarium access we have through Makata Middle School, one of the only middle schools in Michigan that has its own planetarium. And yeah, it's a beautiful setting for us to do our meetings. So nice surroundings to be a successful group. Talking about stars, let's start close to home, or close is relative. 150 million kilometers. And I talk only during this talk in kilometers, not feet. Degrees Celsius, Kelvin, what have you, the metric system. NASA is using that as well. That made one of their landers crash, but that's a different story. The sun is big, 1.4 million kilometer diameter. And if we would fly with United Airlines around the sun, it takes about 6 months. About 1 million volumes of the Earth fit into the sun. It's called what we call a G-type main sequence star, and I will explain that later in a diagram. Core temperatures is about 50 million K, and the surface is about 5,800. That's why it shines yellow from our perspective. It converts a lot of hydrogen into helium. And as Louise said, about 100 years ago, people did not know how the sun was powered. They still thought that people with flames were doing that. It has also what they call a differential rotation. So the poles and the equator rotate in a different sequence, which luckily is not happening on Earth. And it takes a lot of time for photons to get out of the core of the star to the surface, 30 million years, which is surprising, but a lot of the energy is also getting out of the sun with neutrinos, which do not have any object of flying through everything, including us. And what astronomers call the sun is a population 1 star, which has some element traces. Why they don't call a star that has no traces a population 3 star, I don't know. I would call it a population 1 star, but that's the way it is. Here you see a comparison of the sun with the rest of the solar system. And you can see that Earth is tiny compared to the sun. Even a solar spot is bigger than Earth. Just to make sure you have the right perspective, you're there on a tiny planet. So with all our disputes and things that are going on, this is it. Not even a sand grain on a beach in Michigan. It's really tiny, our planet, compared to the sun. And also talk about the rest of the universe. So talking about star evolution, it's actually pretty simple. As Louise already said, we have dust and gas clouds. I will show that later. Stars are formed. Stars go on the main sequence. I will explain that as well. Then life is boring for a star because it churns through the elements to create helium. And then the star ends. So it is not any different from our life. We are born, we live, and we die. What is interesting in the star sequence is the death, because there are 3 possibilities. And that is where the physics is becoming interesting. So there was an Indian physicist who already in the 1930s, Mr. Chandrasekhar, calculated that if the core of a star is less than 1.4 sun core mass, we have a white dwarf. Anything above that, a neutron star, where electrons and protons are squished together to neutrons, or a black hole forms. So if you see that in a picture, we have a star nebula that creates stars. We have two ways: an average star, and that's roughly the size of our sun. And don't forget, 75% of the stars in our galaxy are smaller than the sun. So despite the fact that it's an average star, it's still a relatively bigger star, because most of the stars in the galaxy, our galaxy, and in the universe are small red dwarfs. The next step is a red giant, and I will explain that in more detail. That creates a planetary nebula and then a white dwarf. Or when the star is more massive, so we talk about more than 1.4 solar masses in the core, a red supergiant is formed, which is very unstable. There will be a supernova explosion. And there are two ways, depending on the mass of the core that is left behind, or a neutron star is forming, or a black hole. That's basically the story. So that was a pretty quick presentation. Maybe I have more slides. So this is a very famous diagram, Hertzsprung-Russell diagram. Mr. Hertzsprung was a Danish astronomer, Russell an Englishman. Independently, they discovered the temperature relation next to the intensity. So what they plotted was basically the color of a star compared to the solar intensity. So they said the sun is 1 in terms of luminosity, and the temperature is related to the size of the star, the mass of the star, and the intensity which it burns at the surface. So our star, the sun, is a yellow star, a G star. And if you want to know O, B, A, F, etc., I'm not sure if we can say that nowadays, but O, B, A, fine, girl, and kiss me. So that's easy to remember. So the color of a star, when we also look through a telescope and we see a red star, or a blue star, a white star, a yellow star, based on the color, you can determine the surface temperature and you can measure the luminosity. So you see, and you see that with when you put a stick of iron in a fire, it starts to glow red, and the longer you keep it in the fire, the hotter it gets and the more yellow and white and blue it gets. So this is increasing the temperature. It's also diminishing the time the star exists. Because as you can see here, the lifetime of the star is much longer than the lifetime here. Because those blue and white stars, which are gigantic, are driving the flow of hydrogen to helium in a very fast pace. They burn through their fuel very quickly. Where a red dwarf, here in the below, is very slowly churning through its fuel. A red dwarf star can easily exist for 10 to 100 billion years, where a star like Spica will live maybe 100 million years. So there's a huge lifetime difference based on the star size, and that is related, of course, to the mass. You can see a couple of, so this is what they call the main sequence of stars. And every star will end up at the main sequence list. And it depends on the mass of the core, how it will evolve. You see a couple of examples of giants. and supergiants. So the giants are basically sun-sized stars that are growing, converting hydrogen to helium. The next step is helium to carbon. And then the outer shell is fusing hydrogen to helium. And it will blow up the outer envelopes of the star. That will happen to our sun as well. Don't lose sleep about it. That will be happening in roughly 5 billion years from now. But the outer envelope of the sun will reach Earth orbit at a certain point in time when it happens. So if you take a look at the night sky, you can definitely see Aldebaran and Arcturus. These type of stars are giants, and the supergiants, which will blow up at a certain point in time as supernova. Betelgeuse in the constellation of Orion is a prime example of that. Maybe you read stories in the press about that it will happen soon. Now, soon could be still 1 million years from now. Nobody knows. But that is definitely a supergiant that will explode at a certain point in time as a supernova. And then you have the white dwarfs. So that's also how our sun will end. Sirius B, which is the second star circulating the main star Sirius, which is the brightest star we can see in the northern hemisphere. That star is at the moment a white dwarf. So this white dwarf, Sirius B, is circling around this main star Sirius. So this is a very nice diagram that was plotted about 100 years ago, which makes very clear the evolution of stars, the dependence of the star color with the temperature of the surface, as well as the evolution of a star with what will happen based on the mass and the temperature. Some examples of star clouds that are forming stars right now. Very famous picture, Pillars of Creation, M16. On the left side, you see a Hubble Space Telescope picture made in visual light, because Hubble is mainly visual. On the right side, James Webb, which has infrared capabilities. And with that capability, it can penetrate the gas. So you see here a couple of stars that you do not see on the picture of the Hubble, because it is enshrouded in clouds. But inside those clouds, stars are being formed and shine. That's also why we see the dust. Now, the stars in the cloud are basically bringing this cloud to life and making it visible for us. Picture I took from a dark cloud in our galaxy towards the center of the galaxy. This is called Barnard 143. So this is dust clouds, mainly carbon and silicon. There are stars inside of that, but I don't have a camera with infrared capabilities. But these kind of star clouds are forming stars. Our neighbor galaxy, Andromeda, also here you see dust clouds and dust lanes, mainly in the spiral arms, because in the center of the galaxy, and that's also with our galaxy, all the dust is gone because of the suns formed, blowing the gas away. So the star forming is in the spiral arms. That's also what you see in our galaxy. So here are the dust lanes where there's enough material to form new stars. Prime example, of course, is the Orion Nebula, about 1,600 light years from Earth. So we see 1,600 years back in time. And again, inside the Orion Nebula, stars are formed. This is a way better picture than I took, but this is from a more expensive scope. This is from Hubble. And you can see pointed out the different types of stars. So the orange one is a brown dwarf. The yellow one is a yellow star. And we also find some planets. So they are identifiable by spectroscopic measurements out of the Hubble Space Telescope. And this is inside the Orion Nebula. What Hubble also found in the Orion Nebula is what they call proplets. So these are basically solar systems that are growing out of the dust. When we talk about star formation, and when we take a look at the history of our galaxy as well, gas and dust is located in specific regions, clustered and mainly triggered by outside events like a supernova or a star passing or gravitational influences. A cloud starts to contract. It takes time because the dust is also very cold. It's a couple of K. And if that contraction happens in a star forming, then the first 10, 100 million years, there's nothing else than gravity condensing the star. There are several examples of that where we see, there's a very famous example, a T Tauri star, where we see that only gravitational contraction is bringing photons that makes the star visible for us, but there's no fusion happening yet. So it's purely gravitational collapse and the photons that escape because of the temperature increase that we see that this is happening. And we measure that based on spectroscopic data. You can see from a spectrograph clearly if fusion is happening or not. So this is a very slow contraction based purely on gravitational energy. The next stage, but we need temperature for that. Temperature and pressure. With pressure comes temperature. About 1 million K we need in the center to start fusion. And hydrogen and helium are the two most abundant elements in the universe, created when the universe was created. About 25% is helium, the rest is hydrogen. So at that center, at 1 million K, fusion starts to happen. Hydrogen will convert into helium. At the same time, pressure of gravity starts pushing. Gravity is definitely pushing that star closer and closer together, so the temperature increases until there is a equilibrium between the gravity pulling the star together and the thermal energy pushing outward. So photons are coming out and neutrinos are converting or bringing the energy out of the center of the star. If you take a look, and you saw that in the picture of the Hubble scope, this is what you see happening in nature, where star is contracting, all the material that is not able to push into the surface is being jetted out. Magnetic fields are responsible for that. And then we have a crashing disk where most of the time planets are forming out of that. The picture I put in this morning, because I find that so fascinating. This was in the news about a week ago. This is a picture of a star Wispet 2b taken at the VLT, the Very Large Telescope in Chile. The star is masked, so the starlight is not blinding the scope. And what you see is the disk surrounding the star that is formed. And what you nicely see is a planet clearing out the disk. Yeah? So here is a planet clearing out the disk, and the sun, the star is blocked, the starlight is blocked, so the telescope is not blinded. When that star is formed and that equilibrium is there between gravity and fusion, basically it is a boring life because it starts chewing through hydrogen, making helium. Terminal pressure and gravity are in equilibrium. Things start to get interesting again when the the hydrogen is being depleted in the center, in the core. Because at that point in time, there happens a contraction of the core when helium starts to burn inside of the core. And then you get a contraction of the core. The outside shell starts to burn hydrogen into helium. And that's where things start to become interesting because there's no real equilibrium anymore. And the outside, due to temperature increase because of the burning of the hydrogen into helium, the outside shell starts to expand. And that's where you get the red giant. And that's why at a certain point in time, Earth will be involved in that shell. So this proto-proton capture was basically fully clear in the 50s and 60s. Reason was that the proton, the neutron was not seen until the 30s and the 40s in accelerators. So hydrogen converts to deuterium, then goes into a 3 helium, leaving here positron and gamma rays and neutrinos. Same happens here, and then 3 helium fuses to 4 helium, leaving hydrogen again. So that's the core reaction that happens in every star at the start. Our sun is capable of making the next step when helium is burning in the core and that contraction is happening. With that contraction, temperature and pressure are increasing. The next step is making carbon. After that, nitrogen, carbon again because it loses positron, and going into nitrogen and then oxygen. The sun will not go any further than carbon because of the mass, the amount of fuel available, and the temperature. There is not enough mass to crush it further down to make nitrogen and oxygen. We also see what we call carbon stars out there, which are very dark red, beautiful to see in a telescope, where due to turbulence, carbon out of the core is being driven to the surface of a sun. And it's, again, beautiful to see, very dark red, very dark red star. So as I mentioned, the sun will not go any further than carbon fusion. Stars that are more massive, that will collapse into a neutron star or a black hole, will go further. And that's where you get what they call multiple shell burning. So like an onion, a star has different layers of different elements. I mean, it looks beautiful in the picture here. In reality, there's way more turbulence going on, and it will not be a clear-cut shells, but at least it gives a picture of what's going on. And as I mentioned, the outside shell will be hydrogen burning and fusing, then helium and carbon, and then other elements depending on the mass of the star, the mass of the core, because again, there needs to be enough mass to contract that core and to make sure the temperature is high enough to make that burning happen. remember the picture because we will see that same status with neutron stars and black holes. To stay with the first dying scenario, that of a white dwarf, as soon as carbon forms, the core contracts even more and heats up because it needs that heat to keep stable and continuously helium converting into carbon. The outer shell is hydrogen converting to helium, and the temperature is increasing. And at a certain time, that outer shell will be blown off. Because when helium and carbon fuse, a lot of neutrinos are coming out of the core of that star and blowing basically the outer layers of that star away. And that's what we call a planetary nebula. And a beautiful example of that planetary nebula is the Cat Eye Nebula. So here you see the star, basically you see the naked core of the star here, and you see beautifully how the outer layers are blown out, and depending on the color, so red is hydrogen, blue is oxygen, yellow-green is nitrogen. You see beautifully, based on the colors, the elements that are formed in that planetary nebula. And then we come to the white dwarf stage, where inside that planetary nebula, the core of that star is left. That's what we call the white dwarf. The mass is less than 1.4 solar masses, and it will not be able to collapse more based on that mass. Mr. Chandrasekhar, as I mentioned, an Indian physicist, calculated in the 1930s that based on quantum physics, what they call electron degeneracy will not be able to collapse the star more. So that's a quantum effect. You probably heard about the Pauli exclusion principle, where Mr. Pauli states, and that is proven, that no electron can have the same state. That's why around elements, orbitals of our electrons are formed. And that was in the beginning of quantum mechanics, not clear why an element with electrons being negative and a positive core, why that would not collapse. The Pauli principle states that every electron has a specific orbit and a specific shell to evolve around an element, and no electron can be in the same status. And that's also what the pressure of electrons, the more you move electrons closer and closer together, the more they start to move. And Chandrasekhar calculated that up to 1.4 solar masses as a core, that situation is stable, and it will not further collapse. It will collapse when the mass is higher, but we come to that because then we form neutron star. So it's very heavy, a white dwarf, about 10 tons for a teaspoon. And every star basically cools down because at a certain point in time, the hydrogen, the helium, and the carbon is all done. And from a white dwarf, it will go into what they call a black dwarf. So to summarize the first stage of a standard star like our sun, we basically start here on the main sequence of the Hertzsprung-Russell diagram. The sun has still about 5 billion years to go. We'll go into a red giant. The outer layers of that star, so also our sun will go into a planetary nebula, and then basically the star goes into a white dwarf stage and gets cooler and cooler and cooler. Any questions so far?
So in the case of like white dwarf eventually having no energy, becoming a black dwarf, what about, I understand that closer in planets would get consumed when it becomes a red giant or, yeah. But what about the outer planets? Like, let's say in a case of our sun, Neptune, will it continue to orbit then the black dwarf?
Yes, it will continue to orbit. And the question is, depends on the mass of the sun that is left, of the core that is left, if those, if that will shrink. So if you have the sun's core as a white dwarf, then the planet, the red giant will expand and it will form a planetary nebula. So that will move outward, because any planetary nebula we measure now or measure in 100 years, we still see the expansion. There's nothing that stops it. So that will happen to our sun as well. Planetary nebula will go outside and move through the solar system. It's a little speculation from my side, but depending on the size of the core, it could be that Jupiter and Saturn are moving more inside and closer to the left core of the sun, but they will remain in orbit. It's probably for sure Mercury, Venus, probably Earth that will be enveloped in the outside of the sun as in a giant star stage. And from Earth, there will be nothing left in the center. But the other planets will continue evolving around the sun.
I have two questions. I don't see brown dwarf up there. Is it the brown dwarf same as a black dwarf?
No, the brown dwarf is really I would say a stage between a big planet and a star. Jupiter, in our case, is not big enough and does not have the right core mass to start fusion. But if you have a planet that is a little bigger than Jupiter, because Jupiter and also Saturn mainly consist out of hydrogen and helium, if Jupiter would be bigger, it could be that at the center fusion starts, and that would be called the brown dwarf. That's a very low temperature star, and they are very difficult to detect because they're so low in terms of their power, their luminosity.
My second question is about pulsars. Are those neutron stars that aren't quite large enough to be black holes?
Will be the next 3 slides from now.
Oh, sorry.
Other questions?
Thank you. One of the things that's currently under study is what is the relationships between CMEs or coronal mass ejections, and where do they fit into this whole process that they seem to be increasing? But again, is this just normal variability of a process, or in fact, is this signs of a significant change in the process?
Yeah, then we talk about our sun. So our sun has what they call an 11-year cycle with maximum and minimums. So when the cycle is at the maximum, which is this year, 2025, 2026, then the amount of coronal mass ejections are higher than normal. You also see more sunspots. That's why we have aurora last year, this year, last weekend. So that increased activity is in relationship with the coronal mass ejections. And that is all related to the magnetic fields of the sun, which change polarization every 11 years. So north becomes south and vice versa. We don't know why, but it happens. And that causes that increased activity. So that's an 11-year cycle that it happens. Yes.
Any other questions? Yes, one more.
don't know if you'll get into it or not, but are we gonna talk about magnetic fields? And the stars have, not like we have one magnetic field. Stars might have several, at least.
No, not that I'm
Yeah,
aware of. They have sunspot. Well, I mean, if we took a look at the sun has sunspots where magnetic fields are active. But the sunspot is darker and more related because of material moving into the sun because of the magnetic field. But at the end, when you take a look at the sun from far away, like Earth, we still have a north and south pole.
Okay.
But again, we with the sun in this case, I mean, it is not as simple as the Earth magnetic field. With a star, because of the plasma that is creating the star, basically, you have all ions and electrons and protons floating around. You have, let's say, different distributions of magnetic fields around the surface, but it is still related in general to the main north-south axis of the sun. Yeah.
Rules of magnetism.
Okay.
Any other questions? Carl?
Let's get into the more exciting, or at least for me, more exciting stuff, which is neutron stars and black holes. So on the left side of this picture, you see the flow that we discussed so far. Star-forming nebula, a mid-sized star like the sun, and a red giant. So the outer envelopes of the sun or a star growing into a red giant. Arcturus is a prime example. We have planetary nebula, where we see that the outer envelopes of stars are being flown into space. And then we get a white dwarf and red dwarfs or brown dwarfs, because you can see a brown dwarf as a pre-stage of a red dwarf, depending on size and mass again, but they're very difficult to detect because they're not very bright. Goes into a blue dwarf, and the reason is that there's still contraction going on in a red dwarf that will increase the temperature. And then we have basically a naked core of a star, and that is a white dwarf. And that slowly, and it takes billions of years, will get lower in luminosity. If we talk about high mass stars, so stars that are 30, 100 times bigger as our sun, Spica is one example, and Betelgeuse is a red supergiant that is the start for a supernova at a certain point in time. The Crab Nebula, exploded star in 1054. The Chinese and Arabic astronomers noted that event, and that star was even visible during daylight. The last time that happened was in 1604. So we're way due for something like that to happen. But then you get a supernova, and after that, depending on the size of the core and the mass of the core, you get a neutron star or a black hole. So on neutron stars, which is an interesting story, because in the 30s, as I mentioned, Mr. Chandrasekhar calculated that there is an end to that electron degeneracy, avoiding a star collapse. The reason is Einstein, because everybody knows that there is no speed beyond the speed limit. So he calculated that at a certain point in time, electrons are moving that quickly that they reach the speed limit. And what happens after that? Then the element or the electrons are moving so quickly, the pressure is so high that they basically fuse with a proton into a neutron, and a huge amount of neutrinos is coming out of that reaction. Then it took about 40 years, almost 50, for Jocelyn Bell to see in radio emissions a star or an object that, like a lighthouse, beeped every time in a radio emission. She called it LGM1, LGM for Little Green Man, because they thought at that point in time, maybe that's a signal from an alien, until they discovered that this was what they have been looking for, a pulsar, which by coincidence has the beam where it the energy is floating out of the system is directed at us. Because if the beam is up there, we don't see it. Very dense, and the fastest spinning pulsar up to date is PSR, etc. 760 times per second. Earth takes a day. This neutron star 716 times per second to rotate, which means that at the surface it reaches 25% of the speed limit. So this is how a pulsar looks. That was your question. So you see the spinning axis of a neutron star and a very strong magnetic field around a neutron star. And this is the beamed radiation from a neutron star. And again, this beam needs to be directed at us like a lighthouse so we can see and measure the pulsar and with that the timing. Talk about the size. Neutron stars roughly a little bigger than Lansing, our capital. And here's a comparison between white dwarf with half the solar mass and about 6,000 kilometers in diameter. And here's a neutron star. So you can imagine what the pressure is inside the neutron star. And it is basically logic from a quantum mechanical perspective that everything is crushed so that protons and electrons are forming neutrons and neutrinos are escaping to keep the temperature stable. So also here there's an equilibrium between gravity and thermal energy. For this to happen, we need more energy and we need more elements being formed. Because with the carbon stage that our sun reaches, the core temperature and the core pressure is not high enough to make a neutron star or a black hole. You would need to squeeze the sun into a peanut to make a black hole, which will not happen, I hope. So here we go from carbon and helium to oxygen. Oxygen and helium is neon. Helium and neon to magnesium. And again, that happens because of pressure and because of temperature. You get the next stage into fusion. And as long as those fusion steps generate energy, that equilibrium between energy and gravity is maintained. We go all the way to iron, between carbon and oxygen. Silica, oxygen makes sulfur, and two silica make iron. And iron is the end of the road. Why is iron the end of the road? Because after iron, no energy is generated anymore out of fusion. All the elements beyond iron create energy with fission, but not with fusion. So when the core temperature and pressure is so high that iron is generated and all the other elements are gone, iron is left in the core, there's no energy generated anymore in the core. Well, guess who wins? gravity wins. Gravity wins because the core collapses. It cannot sustain anymore that thermal energy to counteract for gravity. The core collapses. With that, a huge amount of neutrinos is coming out of that neutron star or to-be neutron star, and it blows away all the outer pieces of the star. And during that process, further elements are formed from oxygen to rubidium. And if the core of that star is more than 15 solar masses, it will form directly a black hole. It will not go into a neutron star stage. So you have that, let's say, onion shell of different elements. The core, being iron, cannot maintain that thermal equilibrium, so gravity wins. Neutrinos come out of the core and blow away basically everything except the core that's left over. So here the core is left over, all the outer layers are blown away, and this is the onion shell of elements where iron is in the core. We have beautiful examples of supernovae. The last one that we saw in the Large Magellanic Cloud was 1987. This was the star before. This is the star after. As you can see, the star after the supernova explosion outshines basically the entire galaxy. And that's what we see on a regular basis in galaxies, that sometimes stars pop out, and we can see on the spectrum of those stars what they call supernova type 1, very nice peak and a slowdown in slope. And from that peak and slowdown, they also can measure the distance. That's how they found out that the current universe is accelerating. This is the current status of supernova 1987. So you see a nice ring of material plowing into the gas of the universe and heating up the gas. So that's what you see in X-ray. And in infrared, you see all those knots of gas, again, plowing into the gas of the universe. Of course, the famous one is M1, the Crab Nebula, which is a neutron star, a pulsar, which is right here in the middle. And you see here, there's a Xander X-ray and James Webb picture overlapped. So you see beautifully all the remnants of the star envelope, and here you see the swirling of the quickly rotating pulsar and the magnetic fields dragging along the surrounding area. So you see nicely all the swirling of the gases around that neutron star. There are some extreme examples of neutron stars, and in this case, they call them a magnetar, because the magnetic field is extreme. We talk about 1 trillion Gauss. I think the sun is 1 million. So that's way more magnetized, the most magnetized object ever found so far. Rotates every 7.5 seconds. It's on the other side of the galaxy, 43,000 light years away, which is good because there happened in 2004, there was a measurement done where they found basically what they call a star quake. That was a realignment of magnetic fields on that neutron star. If that would have happened not at 43,000 light years, so on the other side of the galaxy, but in our neighborhood, only 10 light years away, we would have not existed anymore. I would have not been standing here. Reason being that the amount of energy and particles coming from that explosion is so huge, it would blow out our ozone layer and it would blow out the oxygen out of our atmosphere. So just to make you aware. Any questions so far before we start into our black hole adventure?
Yeah, I have a question about neutrinos, because I was under the understanding that neutrinos have almost no interaction with other matter.
That's correct.
So how can it be that the neutrinos blow away the shell of the star?
And it is the energy they carry, because neutrinos are not interacting with any matter. They have themselves a very low mass. We talk about 50 electron volts, which is very low, but they still carry a lot of energy, and they carry that energy with them out of the star. And because they don't interfere with anything else, that is for the star core also a very efficient way to get rid of the energy.
I was wondering, how does this whole process relate to travel in space? And the other kind of thing I was interested in is if mining of elements would be feasible in traveling in outer space, and where would they target to go to get the elements?
And what you mean by the question is radiation, probably, or yeah, I mean, and that is one of the biggest hazards for humans in general in space. We are lucky that our atmosphere is blocking the most violent lights, certainly the shortwave UV and shorter wavelengths. If you go outside of the atmosphere, like the astronauts that are circling in the ISS, when there is a solar eruption, they are hiding in specific compartments in the ISS that are more shielded than other compartments in the ISS to avoid the radiation. That will be a challenge for humankind in general when we go to Mars or wherever, to block that radiation. And the most efficient way to do that is with water, to have an outer shell of water, but that is weight. That's a problem. That is a problem. Yeah.
Bill?
The majority of energy is in a star. It comes from helium, hydrogen being converted to helium. How much more energy is released in working from helium to iron?
A lot more, but it takes time. But the majority in terms of gas that is available is helium and hydrogen and helium. So that takes basically the longest time. That can take billions of years, depends on the size of the star. And the last stages, so beyond carbon all the way to iron, is a shorter time because there's less material available. How many more millions of billions of years? I don't know.
Any other questions? Yes, go ahead.
I think the question that I had was, how does the so-called galaxy pulse affect Earth's magnetosphere?
Sorry, can you repeat that?
The galaxy pulse that you described, it goes by different names, but the collapse of the magnetic scar gave that huge pulse of energy throughout our galaxy,
Yeah,
affecting our magnetic sphere, so to speak, around that, and how that's going to affect us.
yeah. And I mean, in that respect, there is a continuous stream of particles bombarding our Earth, not only from the sun, but also from the universe. Sometimes very harsh radiation. And a lot of particles are coming in the form of muons, which are more energetic electrons. The generation of those particles, most think comes from black holes and neutron stars or mergers. Yeah, and we're lucky with our atmosphere. That's also the reason why certain detectors are put in mines several miles down into the earth. So the earth is being used as a shield to get rid of those particles. But yeah, you are bombarded. I mean, you don't see it, but billions of neutrinos are passing my body at the moment, every second. No. That would basically not, because the magnetic field as well is created by the iron core of the earth, and flows of material in the mantle. So we will not use our magnetic field. It is more that the atmosphere and our elements in the atmosphere are being disintegrated because of the high energy that hits the ozone or the oxygen.
Other questions at this time? Let's move on.
Okay, black holes. And I promised Louise to do a specific presentation on black holes next year. So I will only touch a little bit on the subject. And interestingly enough, from a theoretical perspective, thinking about what would happen with light when you have certain masses or a certain gravity that started surprisingly in the 1780s with Mr. Pierre Laplace, a Frenchman, and John Mitchell. But they thought vice versa on what the thinking is now. They were thinking, how big should the sun be and the mass of the sun before light cannot escape anymore? So they did not go the other side. How small should it be and how much mass do you need in a core to avoid light from escaping? The person that gave, of course, the biggest push in that is Einstein with his relativity theory on gravity, where he showed that gravity wrinkles space, and basically space moves as gravity moves, and gravity moves, or light moves, as the space is curved. Karl Schwarzschild, a German, calculated based on Einstein's theory what the surface area of a black hole should be, how that looks like in terms of calculations. And that's why we call the event horizon in a black hole still the Schwarzschild radius. And then Oppenheimer, that was the same Oppenheimer that worked on the Manhattan Project, calculated that basically when there's enough mass present, a star will collapse into a black hole. This was all theoretical work, and a famous English physicist, Eddington, said that nature would prevent those kind of absurdities to exist. Well, he was wrong. Mr. Wheeler coined the term black hole in a presentation he did in 1967. That was all still theoretical. And in the 60s and 70s, nobody really believed that black holes could exist. And how could we measure or see them? Because if a black hole is absorbing everything, including light, then how can we detect them? Until the 70s, when Cygnus X1 was confirmed as a black hole, and I say confirmed because it was based on measurement of radio waves and X-ray, that they saw that something peculiar was with that object, and they could not explain how so much energy could come out of an object like that. Roger Penrose and Stephen Hawking in the 70s worked their physics on singularities. That's also why Penrose got in 2020 the Nobel Prize. Stephen Hawking passed away in 2018, so he was not able to get part of that prize because Nobel prizes are not given to people that are passed away. But they calculated singularities, and they calculated what should be visible in terms of a footprint when we observe the skies. And also Stephen Hawking is probably most famous for calculating the fact that black holes evaporate and that they radiate what is called Hawking radiation. And well, that's what made him world famous. The first real detection of black holes based on physics, based on quantum mechanics, was done in the United States in 2015 with the LIGO observatories. You probably know that there are two observatories, one in Washington and one in Louisiana. And they measured, when they started in 2014, several things, but they were not sure. And in 2015, there was really a very clear signal of two black holes merging. One was 29 and the other 36 solar masses. The speed of their orbits before merging, so the last 5 orbits took 0.2 seconds, 50 times more energy than the visible universe was released, and there was a black hole left with a mass of 62, and 3 solar masses of general gravitational energy was released, and that's what we measured at LIGO. So this was the first proof, real proof that they existed in terms of measurement. This picture is probably very familiar, or that's what was thought of how a black hole looks like. And nobody, when you ask, if somebody tells you he knows what a singularity is, nobody knows. Basically, we call it the singularity, and Roger Penrose and Stephen Hawking calculated a singularity. But inside a singularity, basically all our physics breaks down. If that's the Einstein relativity theory or quantum mechanics, at this point in time, we do not know what is beyond an event horizon. So a different picture, which shows what we see around the black hole, because again, a black hole you cannot see because it is black. All the light is absorbed because the gravity on the surface is so high that light cannot escape. I mean, every body, so Earth, Sun has an escape velocity. I think for Earth it is, 9 or 11 kilometers a second. So for a black hole, basically the escape velocity is the light speed. So nothing can escape a black hole. We see around a black hole a photon sphere, where basically before the material goes into a black hole, it radiates energy because the speed of those particles, those photons traveling around the black hole is high, and therefore it creates energy. You see the event horizon, so nothing can escape that event horizon. Once you are past the event horizon, you're in the black hole. That's it. There's an accretion disk around the black hole. And there's also relativistic jets, where material that is not absorbed by the black hole is jetted out. Those jets can be sometimes light years long. And that is also related to the spin of the black hole and the magnetic field. So that proton sphere, here are the particles swirling around, and the more you get outside the black hole, of course, the slower that rotation is. In another picture, and I will, in the slide after this, you will know why I show this. So here is that ring of photons just before entering the black hole, and you see the disk around the black hole. The disk on this side, on the top side and the bottom side, is distortion because of gravity distorting our view That's like any gravity distortion, where light is bended around an object with a lot of gravity. That is light distortion from the back side and the front side of that accretion disk around a black hole. And that's because of the, again, the distortion due to the high gravity. You see also swirls on the outside and inside. That's depending on the speed of the particles going around the black hole. So this is the signature in terms of light that we can see. And this picture was proven with the Event Horizon Telescope collaboration. This was published a couple of years ago. They did two pictures, one picture of M87, which is a giant galaxy that is part of our galaxy environment. And we are all, so the Andromeda galaxy and our galaxy and the galaxies around it are all attracted to M87. It's called the big attractor. That's also because the inside black hole of that galaxy is 6 billion sun masses. So here you see the picture that the Event Horizon telescope made with the event horizon here, and here the gas swirling around that black hole. And that was next to LIGO, a prime signature of black holes really existing. The other thing that was measured over the last 15 years with big telescopes like the VLT and others, this is Sagittarius A star. That's the center of our Milky Way. And they measured during 10 to 15 years the stars rotating around this center. So they took every 6 months pictures of those stars and were able to see how those stars were rotating around the center. And based on the trajectory and the speed of that rotation and the masses of the stars, they could calculate the mass in the center of our Milky Way and basically confirm that that is also a black hole. So we are 23,000 light years away from the center of our galaxy, and the mass based on the trajectory of those stars about the black hole, 4 million suns is at the center of our galaxy. So it took a long time, but we basically now are sure that black holes exist. What is getting weird is what black holes do. I read a very interesting book from Brian Cox about black holes. I can recommend it. And basically he states that if we understand black holes, then we also understand how the universe evolved, because that is basically both a singularity. And since we do not understand singularities yet, that is a problem. We have a very good theory from Einstein about gravity that works, that is over the last 100 years proven time and again. Your GPS also from your phone depends on that theory. Also, my shirt shows the all over mathematical equation of the standard theory of quantum mechanics. That also works beautifully, but we have two pillars. We don't have yet a combined theory of quantum gravity. And that's what we need for black holes, because there's some really weird stuff going on. If we are in a spaceship looking at a black hole from a safe distance and we see another spaceship flying into the black hole through the event horizon, it never happens. Time stops at the event horizon. We never see the other spaceship go into the black hole. Because of gravity, time stops there. The person in the spaceship flying through the event horizon. His clock is ticking. He's flying through the event horizon. He doesn't notice anything. When he passed the event horizon, he will be spaghetticized. That's a problem, but from a time perspective, he doesn't know anything. Then Hawking radiation. So in quantum mechanics, space, the universe is constantly bubbling. Particles are coming in and out of existence. Hawking calculated when two particles, virtual particles, are popping up at the event horizon, then it is possible that one particle goes in black hole and the other one out. That is basically a radiation. That's how you evaporate the black hole. Now, to evaporate the black hole, that takes more time than the universe exists up till now, but it will happen eventually. Black holes are also cooler than our universe. If you can measure the temperature, it's cooler than the universe, so the evaporation will go very, very slowly. Talking about information, and that was one of the, and is still one of the big discussion points on black holes, like thermodynamics, energy is preserved as one of the standard pillars of science. Also, information is preserved. If I take this laptop, I won't do it, but if I smash it against the wall, then basically, if you're patient enough, you can rebuild the computer and the information is preserved. What happens with a black hole? When all the information, stars, everything else, goes into a black hole. How is information preserved when black hole is evaporating? And it turns out that the surface area of a black hole is determining the information preservation in Planck units. So if we talk about the volume of this room, we can calculate what the volume is based on the size of the room. We squeeze that room to a smaller room, the density will increase. And we talk about the volume. With a black hole, you do not talk about the volume of a black hole. It's the surface area that determines the size and information content of a black hole. Entanglement, also a very interesting quantum effect where Einstein said spookiness at a distance. Entanglement is again proven with several experiments. If you have an electron with a certain status, let's say a spin up, and there is an other entangled electron, doesn't matter where it is, if you measure here spin up, the other electron will have spin down. If you measure here spin down, the other one will have spin up. So there's a correlation, which we do not understand, which also seems to involve black holes in terms of preservation of information. And then in the late 1990s, Leonard Susskind and Gerard van 't Hooft, who was a Dutch guy, came with a calculation where basically we can calculate a black hole like a hologram. A hologram, you know, is basically a two-dimensional picture, which you see as a three-dimensional figure or landscape or whatever you draw. Those same calculations and basics can also be used to describe black holes. If that is correct, that is still speculation, then it could be that space and time are not fundamental. This is basically a teaser for the black hole presentation. But it's very interesting. What is also very interesting is some results from the James Webb Space Telescope that came out a couple of weeks ago. the James Webb did a lot of measurements, and it has a perfect camera for infrared. Main reason is so it can look deep into our universe. And what it found is a lot of these kind of objects where everybody was puzzled what it was. And there were a lot of them. You can see from the Z, which is the redshift distance, so it is related to distance. The higher the redshift, the farther away in time and distance the object is. So these are all objects between 8 to 12 billion light years from Earth. When they looked with the James Webb spectroscopy, they found that there is no fusion going on, so it could not be a star. What they saw was a footprint of material, gas and dust in a gravity collapse. And it turns out, and that came out in a paper 2 weeks ago, that inside of all those dust cocoons, there is a black hole. So obviously, early in the universe, black holes were formed by the sole collapse of gas and dust that was present after the start of the universe. Because again, this is from 8 to 12 billion years ago. So I thought it was nice to show that. And that we are all stardust, as also Carl Sagan said. If you take a look at the origin of the elements, then you can see that a lot of those elements are formed in our sun or in mergers of neutron stars or in dying stars. So this is all what is created from sun-like stars. Here you see high mass stars blowing out the supernova, and here neutron stars or other stars collapsing. So the gold on your finger is coming from space. That's the story. Thank you for your attention, and any questions, I'm more than happy to answer.
Any additional questions? Yes, hold on a second here.
We hear a lot lately about dark energy, dark mass. Nobody knows what it is or where it comes from or can find it. How does that all tie into the rest of this stuff? Does anybody know?
Everything we don't understand, we call dark. Yeah. And the latest is that everything we see and everything I talked about today is only 5% of the universe.
Yeah.
25% is dark matter, where the latest theory is that it is a particle that is not yet detected and will be very, very difficult to detect because it is only interacting gravitationally. So there are experiments set up in mines to detect dark matter, but like neutrinos, which are also very, very difficult to detect, it could be that we will never be able to detect them. Dark energy, nobody understands. What they found in the 1990s based on supernova explosions is that despite what everybody thought, expanding universe which slows down and slows down because of gravity, it turns out that 4 or 5 billion years ago, that universe started to expand more rapidly. It's nice that they found it and it is confirmed. And people speculate that the lambda in Einstein's formulation, which he said was his biggest mistake, that lambda, which is linked to vacuum energy, quantum energy of the universe, that could be dark energy, but at this point in time, nobody really has nailed it.
Quick question. I understand space is really big,
Yes.
but how does black holes not become a runaway process? Because I get, Hawking radiation, but it's, to my understanding, it's minor. It's ejection of matter, antimatter at the edge of the event horizon. But how does it, like super massive black holes at this core of galaxies, not eventually consume the galaxy and become just a runaway process?
There are two reasons for that, because if you stay on a safe distance from a black hole, nothing will happen. It is that when you get really close to a black hole that you feel the gravitational pull, and then you still need to circulate the black hole. So if you're in a spaceship and you have enough speed, you can pass a black hole. That's also why you see that the absorption of material into a black hole is a slow process. It is not like we have a huge amount of gravity and everything is collapsing in the black hole. That is not happening. It's very slowly circulating with more and higher speeds to the event horizon until it is absorbed. At the same time, there's only a certain amount of material that can be absorbed, because at the same time you have jets out of the black hole where it basically spews out material that it is not able to absorb. So that absorption process is a slow going.
Go ahead.
I have a quick question. I saw on the Weather Channel today that Saturn is going to be visible now.
Yeah.
What's the best thing for those of us who do not have a telescope to just the naked eye? And where should we look in the sky?
You should look in the east, southeast. So Saturn is coming up, Frank, around 10 or so.
Tonight.
9 to 10. It's a clear, bright, star-like object that you see in the east, southeast. So it's clearly visible.
Just a warning is that right now the rings are etched onto us. So even with a telescope, all you see what looks like a white line across the disk of the planet. It'll be a few more years before they start tilting again.
But still, it's a
So
beautiful
don't be
sight. It's a
disappointed.
beautiful sight in the scope.
I do have an easy question for you, Carl.
Okay.
Last year we started hearing about predictions of a supernova in the constellation Corona Borealis or Northern Crown.
Yeah.
I think the dates that were given have come and passed. Have you heard anything lately about new predictions?
No, but that is a different nova, because that star in Corona Borealis, that star has a second star revolving around it, and it is basically absorbing material from that second star onto its surface. And when the amount of material on that core star is high enough, it will explode and blow off the outer layer again. And that repeats again, because then the second star again will get all the material absorbed onto the second star. So that's a different supernova. Yeah, they predicted last year, this year. Seems to be a cycle of 80 years, but it's plus minus a couple.
But if it does happen, it'll be a nice sight.
Yes, because then we will see a star that is not visible with the naked eye all of a sudden become visible, and you see the brightness diminishing again over time. Yeah.
I don't know if you're familiar with him, the Sun Guy. Do you listen to his podcasts?
No.
Okay, he's a guy who's extremely knowledgeable about all of these types of things. There is a daily podcast, or at least 5 times a week, where he describes what's happening with the sun. And then he has a variety of discussions about, the effects of these kind of things. One of the most interesting sidelights over the last couple months is that there's a direct correlation between sunspot activity and earthquakes. And they've been able to establish that there is a very well-defined effect between the appearance of focal aspects of sunspots and the occurrence of earthquakes. So anyway, if anybody's interested in this kind of things, he's very entertaining, he's fascinating, he's very knowledgeable. So I really would recommend that you look up the podcast on the Sun Guy.
Okay, thanks for the tip. I was not aware.
Thank you so much for coming today. Take home message. Space is awfully vast and only about 5% of it is filled. And we heard a lot about it today. Thank you so much, Karl. Hope to see you again.